Mass spring systems and waves in general, actually, are governed by second-order differential equations. They describe physical objects that have mass.
And mass means momentum.
Exactly. Because they have mass, they have momentum. The object doesn't just exist in a spot, it moves powerfully through that spot. If you've ever looked at differential equations, it can just look like a giant wall of Greek letters and constants.
Oh, absolutely. Total alphabet soup. Today, we want to focus strictly on the human action behind those letters. We are decoding the logic of initial conditions for mass moving systems.
And that human action, it isn't just a footnote, it is the core requirement.
Yeah.
Without it, the math is literally incomplete. It cannot predict the future of that spring.
Okay, let's unpack this. Before we start stretching springs and hitting things with hammers, we need to understand why the mathematical law demands exactly 2 pieces of input from us. Not 1 piece of information, not 5, exactly 2. To solve for the system, we need 2 unknown constants, A and B. So why is 2 the magic number here?
Well, it comes down to the fundamental laws of motion and a concept called degrees of freedom. So there is a major dividing line in physics between a first-order system and a second-order system.
Right.
First-order equations, they describe things that just fade or decay.
Like a hot cup of coffee cooling down in a room?
That's a perfect example. To mathematically predict exactly how that coffee will cool down over the next hour, the equation only needs 1 single piece of information from you.
Just the starting temperature.
Exactly. Where the heat is right now. You plug in, say, 150 degrees Fahrenheit, and the math can draw a perfect curve of it cooling down. That is a first-order system.
Because the coffee isn't like building up momentum. The heat isn't swinging back and forth, it's just quietly dissipating into the room.
Right, but mass spring systems and waves in general, actually, are governed by second-order differential equations. They describe physical objects that have mass.
And mass means momentum.
Exactly. Because they have mass, they have momentum. The object doesn't just exist in a spot, it moves powerfully through that spot.
So if a first-order system is like taking a photograph of a parked car, where you just need its location to know everything about its current state, a second-order system must be like taking a photograph of a moving car on the highway.
Oh, I like that. Yes.
Right. Because if I show you a photo of a moving car and ask you where it will be in exactly 1 second, knowing its location on the road isn't enough. You absolutely must also know how fast it is traveling at the exact moment the shutter snapped.
That perfectly maps to the math. To predict the future of that car, or a bouncing spring, a unique mathematical solution requires 2 anchors at time 0, or what physicists call t equals 0.
Okay, what are the 2 anchors?
You need the initial displacement, which is the starting position, usually represented by the letter x, and you need the initial velocity, which is the speed and direction, represented by v.
Position and speed, so the 2 starting coordinates. Where is it and how fast is it going?
Exactly. Now, the differential equation itself, the physics engine we talked about, has its own underlying rhythm. It's called the natural angular frequency, represented by the Greek letter omega.
Okay, omega.
And that rhythm is permanently locked in by just 2 physical realities. The stiffness of the spring, which we call K, and the mass of the object attached to it. The math already knows exactly how fast the system naturally wants to bounce.
Wait, I want to pause on the term angular frequency.
Sure.
Because angular implies an angle or a circle. And I know the math uses radians, which is circular math. Why are we using circular math like sines, cosines, radians to describe a spring that is just going straight up and down in a straight line?
That is one of the most beautiful connections in physics, actually. Think of a bicycle wheel spinning at a perfectly steady speed.
Okay, got it.
Now imagine there is a single bright light bulb attached to the edge of that tire. If you stand right in front of the bike, you see the light going in a circle.
Right, just tracing the wheel.
But if you walk away and look at the bike from a distance, directly from the side, entirely edge on, you lose the depth. You don't see a circle anymore.
Oh, wow. You just see a point of light smoothly moving straight up, slowing down at the top, stopping, and moving straight down, slowing down at the bottom.
Exactly. Bouncing is just circular motion viewed from the side.
That's crazy.
It's called simple harmonic motion. The shadow of a spinning circle is a wave. And that is why the math of springs uses radians, sines, and cosines. The spring is spinning through its cycle even though it's moving in a straight line.
That is so cool.
But here's the catch. While the spring's stiffness and mass dictate how fast that invisible wheel spins, the math cannot tell you where on the circle the light bulb started or how big the wheel is without those two anchors from you.
Initial position and initial velocity.
All right.
Okay, so let's look at the first physical way a human actually interacts with a spring and how the math reacts to that specific choice. The classic stretch and release.
This is the most intuitive way we play with springs, right? You grab the heavy mass hanging from the spring, you pull it down to a specific spot, let's say exactly 1 centimeter below its resting point, and you simply let go.
I just open my hand, I don't throw it, I don't give it a push, just a clean drop.
Right. Let's look at what the math sees when you do that. First, we check initial displacement, our x, because you pulled it to 1 centimeter at t equals 0, x equals 1.
So the position slider is set to 1.
Mathematically, this physical choice activates the cosine part of the general equation. The general solution for these systems is a combination of two waves. It's x of t equals a times sine of omega t plus b times cosine of omega t.
Okay.
When t is 0, the cosine of 0 is exactly 1. So that part of the equation turns on. It allows us to solve for the constant b. In this case, b just equals your starting position, 1 centimeter.
But then we have our second anchor, initial velocity, or v, because I just opened my hand and dropped it from rest. The starting velocity is exactly 0, so v equals 0.
And because the velocity is 0, it completely nullifies the sine part of the equation.
Oh, really?
Yeah, the sine of 0 is 0, so that entire half of the mathematical equation just vanishes, which means our other constant, a, is mathematically 0.
Here is where it gets really interesting to me. I love the mechanics of this. By simply opening your hand, your physical action literally zeroes out an entire half of a highly complex differential equation.
Yep.
The sine wave is gone just because you chose not to throw the mass.
It is entirely at the mercy of your hand. And if we look at the physics of the energy involved, it reveals why this happens. When you pull the mass down and hold it there, you are stretching the metal. You are storing pure potential energy into the spring.
Like pulling back a bowstring.
Exactly like that. The cosine wave is the perfect mathematical container for this because a cosine graph starts exactly at its maximum peak right at t equals 0.
So it starts at the absolute top of the roller coaster hill.
Yeah.
It has all the height, all the potential, but no speed yet.
That's it. The cosine wave models pure stored potential energy just waiting to be released.
Okay, so stretching the spring gives us pure potential energy, activates the cosine wave, solves for constant b, and constant a dies. What if we do the exact opposite?
Okay, I like where you're going.
Like, what if we leave the mass perfectly still in its natural resting place, but instead we introduce violence? How does the math change when we add movement without changing its starting position?
That is the hammer strike, or what physicists call being pushed from equilibrium.
So the mass is just hanging there, resting quietly, and I come along with a hammer and suddenly smack it straight down.
Let's run the math on that action. First, initial displacement, because it is sitting exactly at its equilibrium point when the hammer makes contact, at t equals 0, x equals 0.
Which means this time, the physical reality kills the cosine part of the math. The position is 0, the cosine of 0 is 1, but the displacement is 0, so our constant b is completely wiped out. B equals 0, the cosine wave dies.
Right. But our second anchor, initial velocity, is massive this time. You gave it an immediate violent speed. Let's say you hit it so hard that its starting downward velocity is 2 meters per second.
So v equals 2.
This action activates the sine part of the math, allowing you to solve for constant a. Let's use some real numbers from the sources to see how A is actually calculated here.
Sure.
Let's say you have a mass of 1 kilogram and a spring stiffness, a K value of 9. The natural rhythm, omega, is the square root of K divided by M.
The square root of 9 over 1, which is 3.
Right, so the angular frequency is 3 radians per second. Now the math states that your initial velocity equals A multiplied by omega. So if your velocity is 2 and your omega is 3.
Then A must be 2/3.
Exactly, your constant A is 2/3. The result is a pure sine wave that dictates the entire future of that spring's movement.
Wait, let me push back on this visual for a second. If I hit the mass incredibly hard, it has all this energy.
Yeah.
But you're saying the math models this with a sine wave, and the sine of 0 is 0. How can a wave represent all this massive energy if the graph literally starts at 0? I mean, how could a wave be big if it starts at 0?
That's a really good question. What is happening here is the vital distinction between the value of the wave and the slope of the wave.
Okay, value versus slope.
The value on the graph, how high the line is, represents position. And you are correct, the position is 0 because the mass hasn't actually moved away from the starting line yet in that microsecond. But the slope of the graph, how steep the line is, that represents velocity.
I see.
Picture standing at the start line of a sprint. Your position is 0, but the second the gun goes off, your speed spikes. If you look at a pure sine wave right at t equals 0, the line is crossing the 0 axis, but it is angled incredibly sharply.
It's pointing straight up almost.
Right. It has its steepest possible slope right at the beginning. That steep slope is the math representing that massive 2 meters per second speed you just injected.
So pulling it stores potential energy, which the math models with cosine, starting at a peak with a flat slope. But hitting it injects pure kinetic energy, which the math models with sine, starting at a 0 value, but a massively steep slope.
It creates a beautiful symmetry. The sources summarize it perfectly. Pulling or stretching affects constant B and activates the cosine wave. Throwing or hitting affects constant A and activates the sine wave.
Okay, that is an incredibly clean system, almost too clean. Pure potential energy, pure kinetic energy, pure cosines, pure sines.
Right.
But what happens in the messy real world when our actions aren't so perfectly isolated in the laboratory? Like, what if I pull the mass down 1 centimeter, but instead of just cleanly dropping it, I actively throw it downward?